All right, so let's go with question 2.6. A rigid tank with a volume 83 cubic meters contains 97.7 kilograms of water at 100 degrees Celsius. The tank is heated until the temperature reaches 120 degrees Celsius. Determine the pressure inside the tank at both the beginning and the end of the heating process. So whenever we're given a volume and a mass, that should raise some red flags in a good way. Of course, it's telling us that we know the specific volume, or at least that we can calculate the specific volume. And that's one property we can use to satisfy the state postulate. So in this case, the specific volume would be 83 over 97.7. Okay, so let's write that down. A different one. Specific volume is 83 over 97.7, where this is meters cubed and this is kilograms. And this will, of course, give us a specific volume of 0.85 meters cubed per kilogram. And we're told in the question we're going from 100 to 120. We're also told that it's a rigid tank, and since it's a closed system, the volume isn't changing, the mass isn't changing. That means that this specific volume is the specific volume no matter what we do to this tank. So long as the mass is kept inside, the specific volume is going to stay the same always, no matter what temperature, no matter what pressure. It's always going to be the same. And that's, useful because we don't have to start recalculating it at different states. It's always 0.85. So if we now know that this is 0.85, and we know that the first temperature, that's supposed to be a 1 there, is 100 degrees Celsius, finding the pressure is as simple as looking it up on a table. So let's do just that. Let's go to a table here. And looking at saturated water at 100. So this line here, there we go. This line over here is where we're interested. Now, before we jump and grab this pressure over here, we have to do a bit of a check because we're just assuming that this is going to fall as on the saturated mixture table. We don't know for sure until we check. Now, we look here and we see the lowest and highest specific volume we can have while still being a mixture. In other words, still being able to use this table. And we see that at 100 degrees Celsius, we have to fall within this range of 0.001044 and 1.6729. Now, with a specific volume of 0.85, we do fall into that range. So we're okay, we're good to keep using this table. And pressure is as simple as reading it off from the column, which is 0.10135, which should sound familiar because that's standard sea level pressure. So we now found the pressure at the beginning, and then they increased the temperature to 120. Okay, so again, we go to the 120 entry. We make sure still with the same specific volume, like I said, it's rigid fixed mass, so the specific volume does not change. Sorry, I circled the wrong, this is the pressure. These are the specific volumes, and we see that we are, there we go. We see that we're within the range of 0.001060 and 0.8919 because we're at 0.85, so we're getting really close, but we have a very high quality mixture, but we're still a mixture, so we're okay to keep using this. And it means that the pressure at 120 degrees Celsius is 0.19853 megapascals, so about 2 atmospheres almost. So it's pretty simple, but then they ask again, same thing, but they're heating it to 125. So we go to, I'm just going to get rid of some markings to make it a bit clearer, but we go to 125 and we read the pressure, and that's the pressure for 125, right? No, it's not. Why is it not? Well, again, we have to check that we're actually able to use this table. In other words, we have to check that we're still a saturated mixture. Now, remember, when we did 120, we were still a saturated mixture, but we had gotten significantly closer to becoming a superheated vapor. So maybe at 125, that pushes us over the edge into the superheated region. And if we check the limits, the maximum we can have is 0.77 0.06, and we're above that. And that means that, no, we can't just use this pressure over here. Why? Because this table doesn't work for us anymore. We're not a mixture, we're a superheated vapor. So we have to go now to the superheated tables to find what our actual value of pressure is. And this is where we have to start doing a bit of interpolation, and it gets a little tricky in this specific case. So let's go to our superheated tables. Now, we know we're looking for a temperature of 125, so somewhere between the entries of 100 and 150. I don't know which table because this is sorted by pressure, and it's pressure that we're trying to find. But we know it's going to be somewhere between here, and we're looking in the specific volume column of each table, and we want to see something that encloses that 0.83. Now, if we do that, it's clearly not this table, is way too big. So we go over to the next table. It's not this one. Let me just cross those out. It's not this. It's not this. Okay, now we're getting closer. It's still not quite this guy. And if we go to the next table, it's a bit too low. So it's going to be somewhere in between these two pressures of 0.2 and 0.3 megapascals. So we have to interpolate a bit. Now you'll notice this first row in each table is the saturation temperature. So not the, this isn't necessarily going to be 100 degrees. It's going to be actually this temperature here. So what we want to do is we want to interpolate between these two temperatures being 120.23 and 150. And we want to try to see at what temperature in this scale, we want to interpolate here to find 125 degrees Celsius, and then we use that to find what the specific volume is in this case, okay? Now we know it's going to be a bit too high, but the reason we're doing this is because we're going to do the same thing on this next table over here. So we're going to interpolate between 133.55 and 150. And then we're going to sort of extrapolate downwards below to find at a temperature of 125 what the saturation is. Correction, what the specific volume is. And then once we have those two values of specific volume at 125, then we can interpolate them knowing the pressure here is 0.2 and 0.3. And if you do that, it's a bit long, but if you do that, the answer you should end up with is 211, so 0.211. So it's very close to this table, more than it is to this table. But again, just to summarize what we're doing when we interpolate here, what we're doing is we're taking 120 and 150. Okay, we're linearly interpolating our way to 125 because that's the temperature they tell us we're at. Okay, so that's about a quarter of the distance from this guy to this guy, and that means that the specific volume there is a quarter of the distance between this guy to this guy. Okay, and we do the exact same thing here, but you'll notice, of course, the temperature we want is a bit lower. So we have to, instead of interpolate, we actually have to extrapolate here to a lower temperature. And once we do that, we get our next specific volume. And then with those two interpolated, and well, one interpolated, one extrapolated specific volume, we have to go and then relate that to the pressures 0.2 and 0.3 and see how far in between we are. And what you'll find is that we're just slightly above this 0.2. We're at 0.21 megapascals of pressure.